a topic I really like because it's got a really cool name, eigenvectors and eigenvalues. It may be that some of you remember me or Dr. DeMarcus mentioning eigenvectors and eigenvalues, because indeed we did mention the words, but we haven't studied them in any great detail. Does anyone here remember what an eigenvector is? Okay, well, that's cool. Okay, so first of all, can you put your little yellow hands up? This will be a way of me telling who's actually paying attention. Can you put your little yellow hands up if you can read the screen from the Teams feed? So Cindy can't read it or isn't there, and Joe can't read it or isn't there. Joe, come on. Oh, you can read it. Can you, Cindy? What about you? Are you there, Cindy? Yeah, I can read it. You can read it, so it's not too pixelated. I know you can. It's all obviously. It is all on your. It's all on OneNote. Now, what I've done is you've got a copy of this document in your own area, so you can annotate it as we go if you wish. It's also in the content library. I'll be filling it on as we go. And in a sense, I think it's better if you can watch me, because you can see what I'm pointing at, and you can take paper notes. But whatever it is up to you. Please let me know if any of the technology is letting you down. I can slow down. We're in no hurry. We're probably one of the few schools in the country in further maths. We are ahead of where we were last year. We are easily going to finish the syllabus. Okay, if you can put your hands down now, please. Okay, now when we consider matrices as being transformation matrices, we already know that some matrices map a line to the same line. So you have a line, you apply a transformation to it, and it doesn't change the line stays where it is. Lines like this are called invariant lines under that matrix. So any given matrix will have some invariant lines. Here's an obvious one, a stretch parallel to the x-axis. All horizontal lines will be invariant lines. Right now, if you're on a horizontal line and the line is stretched parallel to the x-axis, that will be an invariant line. A reflection in the line y equals x, a matrix that represents a reflection in the line y equals x, the line y equals x will be invariant. And if you're in 3D, if you've got a 3 by 3 matrix, say a rotation about a line, easiest to visualize rotation about an axis, that axis will be invariant, but other lines won't be. Now, sometimes when you have a line like if you have a reflection and you reflect through that line, the points on the line stay exactly where they are. So not only is the line invariant, the points on that line are invariant. Sometimes an invariant line, the points move along the line. So if you have a stretch parallel to the x-axis, for example, points on the x-axis will move. Now move on to another point on the x-axis. So the x-axis has stayed where it is. So the line has not changed, but the points on the line have moved. Ben, I see your hands up. Is that a new question, or is that left up from last one?
No, so I just got to take it down to last one.
Yeah, that's fine. Okay. Are there any? So I can see the yellow hands. If you don't want to shout out, if you put your hand up, I'll come to you. Any questions on what I've said so far? Okay. If each point on this line is mapped to itself, what's that called? What's a line called where all the points on the line stay exactly where they are? There's a name given to it, and you have studied this. We studied this at the end of last year. So you should remember. Yeah.
Points.
Say again.
Line of invariant points.
Line of invariant points, exactly right. Okay. So line of invariant points is a certain form of an invariant line, but really important to realise an invariant line does not mean the same thing as a line of invariant points. Okay, now this we're going to recall something we've done before, which is I want to find the equation of any invariant lines of this matrix. Now, the thing we're going to do slightly differently, you need to be able to do both. I'm specifying here, I'm only interested in invariant lines that go through the origin. Okay. So can anyone establish what working I need to do? You know, I've left some spaces there. How do I find out the equation of an invariant line that goes through the origin of this matrix? And here's my starting point. Obviously, I've got to fill something in there. So if anyone either wants to shout out or put their hand up so I can come to them.
The middle, and then x dash and x dash on the right side.
Okay, who said that?
Ethan.
Thank you, Ethan. It's just me and you then. Okay, wonderful. Okay. So if it's a line through the origin, it must be.
Isn't it x?
It is. Yeah, thank you. It must be that its point is x, it's got coordinates x and x. If it's an invariant line, a point might go to a different x coordinate, but if it's the same line, the line hasn't changed, the gradient isn't changed, so it must look like that. Now the thing we're doing differently, slightly differently from what we would have done last year, is we might not have insisted it went through the origin, so you would have had y equals mx plus c. So this would have said mx dash, and this would have said mx dash plus c. But I've specified I'm interested in lines of the origin for this. Okay, and what you've got to do is solve that. So go for it. If you could solve that and tell me what you get for n. Put your hand up if you need any help. Otherwise, I'll just let you get on that. Okay, has anyone got an answer? I've made a mistake. No. Let's see who we've got here. Okay, Joe. Hello, Joe.
M equals a half or M equals minus 1.
That sounds right, yes, I remember that, good. So one bit of reasoning here, there's my working. I had a strange line here, don't worry about that line. It's not wrong, but it's not that informative. It is true for all x. So you've got to think about this, we're not solving to find x, it's true for all x, it's an identity for all x, which means we can say that means that 2m squared plus n minus 1 equals 0. We don't want to say or x equals 0 because we're looking for the gradient that makes it's true for all x. And that gives us m equals minus 1 or half, was it, Joe? All right, so varying lines are y equals x minus x and y equals a half x. So far, no different from what you've done before. Okay, now I just want to investigate a little bit more what happens to points on those lines. So we'll start off with y equals minus x. Which we can investigate by doing it like that. So we'll see what happens to points that have got coordinates x minus x, in other words on the line y equals minus x. And if you work that through, you'll get 4x minus 6, you get 2x, you get minus 2x, you get 2x minus x. So a point on the line y equals minus x has had its x and y coordinates doubled. In other words, it's been stretched, and this is an important thing, it's been stretched. I've said moved, I should have said stretched. Points on that line have been stretched along the line by a scale factor of 2. So they've stayed on the line, but stretched by a scale factor of 2. If you could do a similar analysis, please, for the second one, of the line y equals half x, see what happens to those points, please. I'll pick someone to tell me. Y equals. Okay. Robert, what have you come up with?
I'm not sure. I think it's like half x and
Okay. Let's work this out. What should I?
the first one is x and then the other one is half x.
The x half x, yeah.
Yeah.
So what does that give you when you multiply that out?
I think is not really sure.
Well, come on, have you forgotten how to multiply a matrix? What happens when you multiply this matrix by that vector?
So is it just 5x?
Yes, 5x on the top.
And then 5 over 2x.
Exactly right, good. Now what did we start with? We started with x and a half x.
Yeah, and then like 5.
5. That's it. So again, a point on the line y equals a half x, which has got coordinates x, half x, is still on the line y equals a half x. We knew that already, but it's been stretched along it by a factor of 5. And this is where the sort of interpretation, the next technique, the eigenvectors and eigenvalues I'm about to teach you about, that's really important. You understand that these invariant lines, points have been stretched along there by a scale factor, and we have worked out what that scale factor is, and that's something we didn't do. Well, at least I didn't do last year. Okay. It's worth noting that there are no other. I changed that. I thought I changed that. Okay, so there's. I haven't changed that. Who am I? I'm writing the concept of it. Okay, so no other line parallel. No other line. So there are no other lines through the origin that are invariant. And because parallelism is preserved, now that's an important thing you need to understand. Parallelism is preserved. That means that if two lines start off parallel on the matrix transformation, any matrix transformation, they remain parallel. So what that means is if there's no other lines through the origin that are invariant, there can be no other lines that are invariant, apart from lines possibly that are parallel to the two invariant lines we've already found. We'd only find that by you putting a plus C in there, but I'm not interested. I'm only interested in lines to the origin. So there are no other lines to the origin that are invariant. This other analysis is slightly different. I want to have a look now at the effects of this transformation on lines that aren't invariant. So for example, the line y equals 0, I can write like this, x 0, and that goes to 4x and x. So the line y equals 0 becomes the line y equals a quarter x. So this transformation turns the line y equals 0, the x-axis, into the line y equals a quarter x. If you could now try work out the image of the line y equals x, please. Where does the line y equal x go to? Andy, where do you get the image of the line y equal x?
So you got 6x, 4x.
6x, 4x. So x, 6. So what's the equation of that line?
So that would be y equals to 2 over 3x.
Good, y equals 2/3 x. So the line y equals x is transformed to the line y equals 2/3 x. Does anyone have any questions on that analysis? Because that's something new that you haven't necessarily looked at before. Okay, there's a diagrammatic way of putting all that together. It looks fairly complicated. Can you all see that? Hard to interpret. I'll try and explain what it means. Inside this circle, this shaded circle, the shaded ring, doesn't have any great significance itself, but inside the circle, we're drawing the object lines, the original lines, and outside the circle, we're turning them into the image lines. So, for example, the ones we just did were y equals x. So here's the line, I'm going to highlight in yellow. That's the line y equals x. And we found just now, the one that Andy did, the image of that is y equals 2/3 x. So outside the circle, we draw y equals 2/3 x. That's 2/3 x. And so if we can kind of see what's happened to these lines are getting bent towards y equals half x. Remember, y equals half x was an invariant line. So y equals half x goes straight through the circle. It doesn't change. So all the lines are getting bent towards y equals half x. And interestingly, there's another invariant line, which we got, which is y equals minus x. And the lines, if you like, are getting repelled from y equals minus x. All these other lines are getting pushed away from it. And so it can be a kind of a nice way of trying to visualize the effects of a matrix transformation. Of course, it's hard enough in 2 dimensions. If you can imagine trying to put a diagram together that represented the effect of a 3-dimensional transformation, I think we'd all agree that's beyond my ability to do a drawing of. In fact, I've never even seen it, but you can imagine how you could do the same thing. But it's important that you can sort of follow that diagram. Any questions on that? Any hands up? There's a hand up. No, there isn't. Any questions? Okay, now we're going to develop a more efficient and more developed approach to what we've just done above. So we need some new terminology. The word eigenvector is the direction vector of an invariant line. So if we find a line that is invariant, then its direction is an eigenvector. And it's useful to note that this business about parallelism is important here. If a line not through the origin is invariant, it must also be that the same line going through the origin, translated to go through the origin, will also be invariant because parallelism is preserved. So we can state here that the eigenvector, the direction vector of an invariant line, is the same as saying it's the direction vector of any line through the origin that is invariant. So for our 2 by 2 ones that we just did, we've already got, we found the eigenvectors. The eigenvector of this one, y equals minus x, the direction vector of this line is 1 minus 1. So 1 minus 1 is an eigenvector of this matrix. The direction vector here of this invariant line is 1.5. So 1.5 is an eigenvector of that 2 by 2 matrix. Anyone speak any German? Hands up if you speak any German at all. Wow. Esther does. Okay, do you know what eigen means, Esther?
No.
No, and I'm not actually sure if it... Yeah, and I don't even know if this is a word that is used in everyday speech in German, but it is a German word. It means characteristic. Okay? The eigenvector is a characteristic vector of a matrix. It turns out you could describe matrices by their eigenvectors. So the characteristic vector is what the eigenvector translates as. Though I'm not sure if in everyday language in German you can just say an eigen is someone's characteristic or not. So that's our eigenvector. The eigenvalue is the scale factor associated with it. So the eigenvector, the eigenvalue of 1 minus 1 is 2, and the eigenvalue of 1.5 is 5. Okay. Now this is where we get onto the sort of the A-level stuff. Okay. To find an eigenvector, what we're trying to do is solve the equation, the matrix equation. Matrix times a vector is lambda times a vector. Now I'm just going to bring that back up in a second, but just to show how that relates to what we've done. We here are trying to solve the equation. This times that vector is some multiple of that vector. Comes to the same thing. Because if U is an invariant vector, if U is invariant under that matrix transformation, we multiply it by the matrix. It's invariant, so the resultant vector must be the same, have the same direction vector, but it's some multiple of it. So M mu equals mu lambda. Now that, basically, if you don't fully understand why that is doing exactly the same thing as we've just done, the next few lessons are going to be a complete mess for you. So I wanted to take time for you to think about that. Make sure you understand it. Make sure you understand it's the same as what we've already done. And just raise your hand if you want me to try and go through this more, again, more slowly with some other examples. Once we've understood that this is the critical thing, once we've understood that finding an eigenvector, which sounds like a really fancy thing to do, finding an eigenvector is solving this equation, then we're rocking.
So,
Yes, hello, Belva.
sorry, just to clarify, I'm not so sure if I get it right.
Yeah.
So the eigenvector is the U, is it?
That's absolutely right, yeah. So
Yeah, and the eigenvalue is mu.
that's exactly right. So lambda.
And M is the matrix.
Eigenvector. Eigenvalue. But even without knowing the words eigenvector and eigenvalue, I expect you to be able to see that this is the equation you would solve if you wanted to find what vector is invariant under that transformation. What vector gives you an invariant line? It means the direction vector through the origin hasn't changed, it's just been sort of stretched.
But does it has to pass through the origin?
Yeah.
I
mean, I will come back to my point saying about how, because of matrix transformation, something we may or may not have proved last year, I can't remember, but it's certainly something you need to know. A matrix transformation keeps parallel lines parallel. And what that means is if there is a line that doesn't go through the origin that is invariant, then it would also be invariant if it went through the origin. Which means I'm quite at liberty just to consider lines through the origin. So yes, we are saying that an eigenvector is the direction vector of a line through the origin that is invariant.
Okay. Thanks.
Why do they conserve parallelism?
So I think I proved it last year. I can't remember, and I think you have to do a little bit of algebra for it. But what you will find is if you take any matrix of the form A, B, C, D, and multiply it by x mx, right, and also x mx plus c, any lines with the same m will also transform to something with the same m.
Sure.
Okay. And so that's. I mean, I could do it later on if you like and put it there as an addendum. I don't want to break the flow, but it's a simple piece of algebra. Then there's quite possibly a more sophisticated. It's the nature of linear transformations. There's quite possibly a more sophisticated approach to convincing you that parallel lines remain parallel. But you know, if you think of matrices in terms of rotations and reflections and stretches, all those things would keep parallel lines parallel. But I can do it algebraically. It's a good question. I think I have done it, but I'll do it again as an extra. And the line of invariant points would also be an eigenvector. It would also solve this, but lambda would be 1. The eigenvalue would be 1. Okay. So we're going to try and solve the same equation we've already solved, but using this slightly different approach. So I've got this matrix 4, 2, 1, 3, and I'm going to multiply that by a vector. I'm going to multiply a vector by that, and I want to end up with something that is a vector in the same direction, but a multiple of it. So this equation here should give me the same sorts of results as I got before. I should be finding the same eigenvectors and eigenvalues I found before, which were 1 minus 1 and 2, or 1.5 and 5. So again, put your hand up if that equation isn't clear to you, because that's where it all starts. Everything we do now starts from this. I'm then going to try and solve it. Now, you might be asking what it is I'm even trying to find. Well, what I'm trying to find are u and lambda. They're my unknowns. Let's see what happens. I subtract lambda and u from both sides. I can do that. Now, my next step sort of naively, is to factorise this and write m minus lambda u equals 0. But that's wrong. Can anyone tell me, either shout out or put your hand up, why is this wrong? This line here that I said is wrong.
Because you just try to take away a matrix.
That's good. Who said that?
Casper.
Thank you, Casper. Yeah, that's a scalar. That's a number. And that's the matrix. And so that statement there just does not make any sense at all. So how can I save it? What can I write here that is basically exactly the same that now makes sense?
M minus lambda I.
Exactly right. Good. Who said that?
Okay.
Thank you. Yeah. Okay. We save it like that. And now that does work because the matrix multiplication is distributive over addition and subtraction. It does mean you can multiply out the brackets. This does multiply out to mu minus lambda I u, which is the same as m minus lambda u. So it does work. Okay. Now, we've got a brief interlude. This is something that wasn't covered in the book. It's just claimed, and it sort of slightly bothered me. I want to prove something to you, which I don't think is trivial. Maybe for some of you it's obvious. Maybe it seems okay, and you're prepared to take it at face value. But I want to solve it. I want to prove to you that if a matrix times a vector is equal to 0, which is a matrix or a vector with all zeros in it, I want to prove to you if a matrix times a vector is 0, that must mean the determinant of the matrix is 0, or indeed the vector is 0. Because of the way I'm going to do it, I basically end up proving that the determinant of the matrix must be 0. Now, suppose your matrix and your vector are non-zero. You've got a matrix and a vector that are not 0. You multiply them together to get 0. Then we could say, we could pre-multiply both sides by the inverse of m, and I would get v equals inverse of the matrix times 0, which means the vector must be 0. Now, how does that prove that the determinant of the matrix is 0? Can someone explain how this working here basically proves that the determinant of the matrix is 0? How does that work?
So you said, do you mean the determinant?
Sir, if the matrix has no inverse.
It means, yes, exactly, because this, I was a bit naughty. Whenever you create an inverse matrix, you should specify if it's a non-singular matrix. So exactly right. So that we've got a contradiction, implies the matrix doesn't exist, n has no inverse. Because we've got a contradiction, and if we've got a contradiction, it means something we did was wrong, and it's this step here. So I should add in there, if n minus 1 exists. You can only do that if the inverse matrix exists. If the inverse matrix exists, you get a contradiction, because we said they're non-zero, and we've ended up saying one of them is 0, and that tells us that the determinant of n must be 0. So if a matrix times a determinant times a vector is 0, that matrix must have a 0 determinant. So what we end up with is this, and the most important equation you'll see in this topic, we have found that. We have found the two bars, like the modulus sign, when you're referring to matrix, that means determinant. So I'm going to start using this notation now. That means the determinant of m minus lambda u is 0. And that is called the characteristic equation for that matrix. And you have to be absolutely familiar with that language.
Wait, so I'm not sure what this. Sorry, so I don't quite understand the proof.
The proof that the determinant's 0, the determinant's 0.
Yeah.
Yeah. Okay. So we'll run through it again and just shout out. That was Casper, was it? Casper.
Yeah. I think so.
Keep your mic on and just shout out if I get to something you don't get. Okay. Keep your mic on. That makes it a bit easier. Okay. So we can start off by supposing we've got a matrix and a vector, and we're going to say they're both non-zero. So we've got a matrix and a vector non-zero. And I want to solve the equation mv equals 0. Maybe that's where you're good. To solve, so rather than saying then, what I'm trying to do is solve the equation matrix times vector equals 0. All right?
Yeah.
Okay, now, to solve that equation, well, one thing I could do, I'm going to try and find the vector v. I could pre-multiply both sides by the inverse of m, right? So are you happy with that line?
Yeah.
Well, I've now got a vector is equal to a matrix times 0. Well, a matrix times 0 is 0. So I've proved that the vector v is equal to 0.
Yeah.
But that contradicts with my starting point, which means something I've done there is wrong. There's something there that doesn't make sense because I've got a contradiction. And the thing that I've got wrong, Casper, is I've just said I could pre-multiply both sides by the inverse of m. You can only do that if the inverse of m exists. And it doesn't. It's there or it doesn't exist. M has no inverse, so the determinant must be 0. Yeah.
Sorry, sir.
Yeah, let's go.
About the characteristic equation.
Yeah. Who's can I ask who's speaking? Kelvin? Because I can't see anyone. Kelvin, is that Kelvin? Hi, Kelvin.
Should it be determinant of m minus lambda I?
Oh, good Lord Almighty! Thank you, Kelvin. Well, it's such a polite way of saying you've been an idiot. Thank you very much, Kelvin. That would have the most important bit would have confused everyone. Okay, try again. Thank you, Kelvin. So we've got this, remember we've got our n minus lambda I times u equals 0. From what I've just done, it proves that n minus lambda I must have a 0 determinant. So that's called the characteristic equation. So, well, this is very lengthy, this introduction, I know, but there's not much you can do until we've got through all of this. So, does anyone have any questions? And B, if you would appreciate a few minutes, because I'm afraid I'm going to carry on like this to the end of the lesson, I think, to get to where we need to go, and I won't be doing it tomorrow. If anyone needs a couple of minutes break, just put your hand up and I'll give you a couple of minutes break. If you just need to jump up and down a stretch or anything. Okay, Michael, 2 minutes? 2 minutes is enough. I'm giving you 2 minutes, guys. You can go back through those. So in that 2 minutes, if anyone wants a question. Okay, 2 minutes is.
Sorry, sir. Sir.
Hello.
Sorry. Yeah. I can't quite get it.
Oh, it's nice to see you, Belva. Hello.
Oh, hi. How can you conclude that M has no inverse by proving the contradiction?
So do you remember how proof by contradiction works? So proof by contradiction works if you make some assumptions at the start and they lead to something that contradicts. It means that some step you must have made is not valid. Okay? Which means, and effectively what it is here I have made another assumption I have assumed, in doing this proof, I've assumed two things. I've said three things. I've said M and V are non-zero. I've also assumed that the inverse of M exists. And then I've done that work, and I've proved that V is zero. Okay? So the assumption that M, the inverse of M exists, can't be true. I made this assumption that I could find the inverse of M. That can't be true, because if it was true, I would lead to a contradiction.
But why can't V be zero?
Because I've started off with two non-zero vectors. I'm starting off with M and V. Now, you're right in the sense, Bell, but the other option is V could be zero and the inverse of M exists. But I'm looking for is it possible to have a non-zero vector V that solves MV equals zero? Can I multiply a vector that isn't zero by a matrix and get zero? And the answer is, I can, but only if the determinant of that matrix is zero.
Yeah, I know, but if there is a contradiction, that either means that M has no inverse or the vector is zero.
Okay, all right, do it this way then. Yeah, or the vector is zero. So if I want to solve this equation, I can only solve it if either the determinant of M is zero or V is zero. You're right. But what we're going to be doing is trying to solve it for non-zero V. So how can we solve this equation for non-zero V? We can, but only with a matrix that has a determinant of zero. So let's clearly that equation, the equation I put up, MV equals zero, does have solution V equals zero. Clearly it has solution V equals zero, always has a solution V equals zero, but I'm looking for solutions that don't have V equals zero. And I can get them as long as the determinant of M is zero. Okay, Michael, are you back? Have you had to, are you here, Michael? Yeah.
Yes, I'm sir.
Cool. Okay. So we're trying to solve now, to solve the original equation, our characteristic equation, we need to have the determinant of M minus lambda I equals zero. Well, M minus lambda I is 4 minus lambda 2, 1, 3 minus lambda. So I'm now trying to solve this. This is also a way of writing the characteristic equation. And in fact, it's usual, if you're asked to find the eigenvalues and eigenvectors of a matrix, it's usual to go straight to writing this down as being the characteristic equation. Does everyone understand where this came from? Because I can expand it in more detail if needed. Yes, Carrie.
Sorry, I have a problem with the previous page because, like you said, like the matrix cannot minus the lambda because matrix is a matrix and a scalar.
Yeah.
So without changing the lambda into lambda I, can you just use the determinant of the matrix minus lambda and let it equals to zero?
No, because the determinant, if I've understood you correctly, you are suggesting that you think that the determinant of M minus lambda I, well, let's make it more general. You're suggesting, I think, that you think that determinant of two matrices added together is the same as the matrix of one plus the determinant of one plus the determinant of the other. That's not true.
Yeah, I know it's not true, but I'm not sure why. You said matrix are not minus lambda, so I just changed the matrix into a scalar, so it's the determinant of the matrix, and let it minus lambda. I don't know why it's
because I think it comes to the same thing. So I think what you're saying is determinant of m minus lambda I equal to 0. That's my characteristic. You're saying, is that the same as, say, the determinant of m minus lambda? Is that what you're suggesting?
Yeah, kind of, yeah.
Yeah, and that, do you see, that kind of comes to this. Why do you think the determinant, it's not true. It's not true that x plus y squared is equal to x squared plus y squared. So why should it be true that the determinant of m minus lambda I is the same as the determinant of m minus the determinant of lambda I? Which isn't, by the way, lambda anyway. The determinant of lambda I wouldn't actually be. Actually, can anyone answer this? What is the determinant of lambda I in any case? Because it's not lambda.
It should be lambda.
It's not lambda. Anyone? What would it be?
0.
No? In general.
Last one is lambda squared.
It's lambda squared for a 2 by 2 matrix. It's lambda cubed for a 3 by 3 matrix. For example, what is the determinant of, here's for a 3 by 3. What the determinant of that? Well, it's the same. If I divide each row by lambda, that means I've divided the determinant by lambda cubed, as we were looking at yesterday. So the determinant of lambda I isn't lambda anyway. It's lambda squared or lambda cubed or whatever order matrix you've got. Sorry, Carrie, have I convinced you?
Yeah. Thanks, sir.
Okay, so we're now going to solve this. Yeah.
Why wouldn't that actually never mind, don't worry. Sorry.
You sure? Okay, so we're going to solve our characteristic equation, and we're only doing a 2 by 2 for this. So look, our characteristic equation becomes a polynomial in lambda, which might not be what we were expecting. We're suddenly going to find lambda not used to lambda squared plus 7 lambda, I think, minus 7 lambda, sorry, minus 7 lambda plus 12 minus 2 and plus 10 equals 0. And so we get lambda minus 5, lambda minus 2 equals 0, lambda minus 2 equals 0. So we get lambda equals 5 or lambda equals 2. So remember, this is the same matrix as the one we started the lesson with. We've just approached it very differently. When we did the lesson, when we started off the first time, we found the eigenvectors first and used them to find the eigenvalues, except I wasn't calling them eigenvalues, I was calling them scale factors. Here, solving the characteristic equation, we've in fact found the 2 eigenvalues, but they are the same numbers, they are the same as the scale factors. They're the scale factors we found there earlier. Okay. So we found 2 eigenvalues, and now we need to find the eigenvector corresponding to each one. Well, going right back now to this equation, m minus lambda I u equals 0, we take that equation. So I'm not looking at determinants now, I'm just looking at m minus lambda I u equals 0, and I think it was 4, what were the numbers? 4, 2, 1, 3. So 4 minus lambda 2. So what matrix goes here? what should I put in front of the xy? So I'm going back to my n minus lambda I u equals 0, but I'm using lambda equals 2.
You put m as 2 lambda 2 I.
Yeah, so I'm using that, so n minus 2. So here I'm going to be doing m minus 2I u equals 0. And what is m minus 2I? Well, if lambda is 2, maybe you don't know what I'm getting at. If I write the answer down, then you can all shout out, where does that come from? 2, 2, 1, 1. Okay, so you put your hand up if you want me to explain where that 2, 2, 1, 1 came from. That's the answer I was after. Lucy, right, okay. So Lucy, keep your mic on. Are you happy that what we're trying to do, Lucy, is solve this equation, m minus lambda I u equals 0? You happy with that?
Yeah.
Yeah. And what I've done is I've taken a detour. I've used the results about the determinants I showed you to find that one solution involves lambda being 2.
Yeah.
So what I'm going to do now is I'm going to say lambda is 2, and I'm going to find what u is when lambda is 2. Well, here's our original matrix up here, 4, 2, 1, 3. So when lambda is 2, we've got 4, 2, 1, 3, minus 2 lots of 1, 0, 0, 1. And that's equal to 2, 2, 1, 1, isn't it?
Yeah, okay, that makes sense.
Yeah,
Thank you, sir.
And that gives us, if you look at that, that gives us two equations, 2x plus 2y equals 0, and it gives us x plus y equals 0. And as you will come to expect, they are the same equation. They tell you that y equals minus x. So when lambda is 2, our eigenvector is given by y equals minus x. So for example, 1 minus 1. Now that was the direction vector of the invariant line that corresponded to the scale factor 2 that we've already found. Now, are there any other vectors that I could have put here for lambda 2? Does it have to be 1 minus 1?
No.
So it could have been...
1
Sorry?
1
No, but the lambda is 2 that goes with the scale factor 2. 1.5.
Can be any multiple of 1.
5 minus 1.
Okay, so exactly, it has an eigenvector, 1 minus 1, but also any multiple of 1 minus 1 is an eigenvector. So sometimes it matters, sometimes it doesn't. You'll see it in the book. Sometimes they say find an eigenvector and the answer 1 minus 1 is fine. Sometimes it says find a complete set of eigenvectors, and that would be k times 1 minus 1, any multiple of 1 minus 1. If you trace back through your work, you'll see that if you put any multiple of 1 minus 1 in, the vector direction is not changed. And then we'll do the same for lambda equals 5. So could you do that to see if you've understood? Could you go through exactly the same working? You should actually know what the answer is going to be, but put lambda is 5, follow the same working through, see if you can find the eigenvector corresponding to lambda equals 5. I'll just write down n equals 4, 2, 1, 3. Just remind you what the n was. Okay, Ben, can you talk us through how you started this off? Doesn't matter if you haven't finished yet, or what did you do to
So,
start?
yeah, so it's the eigenvectors minus 1, 1, 2, or 1, yeah, I'm saying minus 2.
Yeah, good, exactly.
And then you get minus x plus 2y equals 0, which gives you y equals a half x, or x minus 2y equals 0, which also gives you the same thing.
So I am happy just to write one of those equations down. If that makes you uncomfortable, write them both down, and you will find in the case of a 2 by 2 matrix that they are the same equation. When you come to the 3 by 3 matrix, you will find 3 different equations, but you'll always find that one of them is a combination of the other 2. So, and we'll do 3 by 3s later on. And so the eigenvector, as you said, was. So I think that would be the easiest way of saying it, wouldn't it? 2, 1. 1 1/2, 2, 1. Eigenvalue 5 as eigenvector. Okay, so we have found 2 eigenvalues for this matrix and the 2 corresponding eigenvectors. And you've seen a completely different approach to how we started off the lesson. It achieves the same thing, but certainly when we get, there's a lot more to it than this. So, you know, this is a new body of knowledge to take on board. Now, what time do we finish today? Is it now? In fact,
I think it's 25 past.
25 past. Brilliant. I'd like it to be. Oh man, that's going to be too long. All right, guys. So I think actually it's now, isn't it? I'm supposed to give you 5 minutes. Isn't your next lesson at 10:25?
No, because I think the next one starts at 30 past.
Oh, okay, fine. Hopefully then, right. See then if you can see this 3 by 3 matrix. See if you can form its characteristic equation and find the values of lambda. I'll stay here. You shout out if you're stuck or if you want to check things at answer.
So,
Yeah.
sorry, did you just said beforehand that lambda is a vector, or is it just a
The
vector?
lambda is a value. So what we've got is for this one we've just done, the eigenvalues are 2 and 5, corresponding eigenvectors are what was it? 1, 1, 1, and 1 minus 1, and guys, the eigenvalues are just numbers.
That it's a factor, so yeah.
Okay, yeah, so and each eigenvalue is paired with an eigenvector. It's not good enough just to say the eigenvalues are 2 and 5 and the eigenvectors are less than this. You've got to make sure it's clear that the 2 is paired with that one and the 5 is paired with that one.
Okay. And also, what do you mean when the v equals to 0?
So v equals 0, the reason I'm ignoring v equals 0 is, remember what we're doing, we're trying to find the direction vector of a line through the origin that is invariant. And if you say the direction vector is 0, 0, you are talking about the origin. The origin is always invariant. So it's the trivial result is that the origin is invariant.
So when a vector equals to 0, that means that it's the origin, is it?
Yeah, because its direction vector 0, 0 means to go along the line, you add 0 to the x and you add 0 to the y, so you stay where you are. So you start at the origin and don't move. So if you have a line with direction vector 0, 0, it's not really a line, it's a point, and it's the origin.
But if the direction vector equals to 1, then what?
But you can't have a vector equaling 1, can you?
Yeah, but it's equal to 0 here. It's not not 0, 0, but it's 0.
Oh, okay. So I'm with you. So right, fine. So where I said where's my yeah, this one.
Yeah.
Okay.
Yeah.
If you have a vector equals 0, what it means or it does mean all elements in that vector are 0.
Oh, so
Yeah.
it can't equals to 1.
Otherwise, I couldn't write v equals 0 without saying, without knowing the dimension of the vector. So a vector being 0 means every element is 0, whereas v equals 1 means nothing.
Yeah.
Yeah. Okay. All right. Yeah. Very, very good question. Good.
Thanks.
Okay, guys, what we'll do is I'll leave you with that. At the start of next lesson, I'll check that you've got that. We'll go through that. Hopefully you'll have finished it by then. And then you're in a position to start trying to practice some of these things for yourself before we look at any more theory. Brilliant stuff. Well done, guys. I say today I should be sending you out instructions. Please read them carefully about how maths is approaching the exams. If you have any questions or problems, do feel free to email me, and I'll see you tomorrow. Bye-bye.
Thanks, sir.
Bye, guys. Bye. Bye. Bye.
Thanks, sir.